Oh, hello. Today's topic is more tan graphing. So it's time to take another look at the tan graph so that we can start sketching them. This here is the basic tan graph, and this here is exactly the same graph, but the text now includes all our transformation variables so that we can see what happens when the transformations occur. There are three attributes that we're going to be looking at when we're thinking about transformations. The first of which is the period. I've got a calculation here for the period, which in this case is pi. We've got the asymptotes, which in our basic case we can see occur at pi on 2 and at 3 pi on 2. And we've got our x-intercepts. We can see here that with our basic case they occur at 0 and at pi. We should notice straight away that the x-intercepts for this basic graph are halfway between our asymptotes. So this value of pi is halfway between pi on 2 and 3 pi on 2. Think about how that relates to our unit circle, and it should be obvious why we have an x-intercept at pi, because when x equals pi we know that tan x equals 0. Let's go back to our graph. First, let's change this a value. This is the dilation in the direction of the y-axis. Have a look at what happens to the period, the asymptotes, and the x-intercepts when I change this. That's right, absolutely nothing. They stay exactly the same. And that's to be expected really, since the vertical transformation won't affect the period or the asymptotes, which are both important properties based on the x-axis. So it won't affect the x-intercepts since the dilation is away from the x-axis, so anything on this x-axis is going to stay exactly the same. Let's have a look at k next, since that's the other vertical transformation. If we translate upwards, we can see that the period doesn't change and the asymptotes don't change, but the x-intercept does. This obviously breaks our assumption. If we have a look at this x-axis intercept here, this breaks our assumption that we noticed previously, which is that our x-intercept is halfway between our period. It doesn't happen anymore. But the x-intercepts are still one period apart. If we compare that x-intercept to that x-intercept, obviously they're going to be a period apart. That's going to be incredibly useful later. Let's reset this k value back to the default 0, and we notice that that introduces the sort of symmetry that we expect, and so our x-intercepts are now halfway between our asymptotes once again. Now let's change this n value, which is the horizontal dilation factor. If the graph is dilated in the direction of the x-axis, that's going to change the period by a factor of 1 on n, as well as move every asymptote away from the x-axis by a factor of 1 on n as well. So for example, when n is 2, which we can get on by clicking that, we can see this dilation happen. This is increasing our n value, which is a dilation in the direction of the x-axis of now factor a half. The period is halved. This value here is now half of pi, as well as every single asymptote is now half of what it was. You may remember we had asymptotes at pi on 2. We've halved that to get to pi on 4. We had an asymptote at 3 pi on 2. We've halved that to get to 3 pi on 4. Compare that. Let's compare that to our original graph. That's what it originally looks like. So we can see that this red graph is our original one, and our blue graph we have dilated by a factor of a half in the direction of the x-axis. The dilation happens around our y-axis, and so that's why we get guaranteed to get this intercept here. Let's reset it back. Now let's change this h value, which is the horizontal translation amount. This doesn't affect the period, but translating everything left by pi on 4 does exactly what you'd expect. Let's compare this to our original graph, which is the red one. The blue has translated left by pi on 4. These asymptotes have also shifted as well, but we can see that our x-intercepts are still halfway between our period because we haven't changed that k value. Having an n value and a k value is particularly complicated, just like in the function study unit. If we've got an n value of 2 and an h value of negative pi on 4, we'll have to think carefully about how that affects it. For example, in the function y equals cos 2 lots of x minus pi on 4, it can be considered dilation of factor a half and then a translation of pi on 4 to the right. Or it can be rearranged to be y is equal to cos of 2x minus pi on 2, which can be considered a translation of pi on 2 right, and then a dilation factor. This will impact on asymptotes primarily, which we will see when we're sketching graph examples. I will put a link to this Desmos. I will put a link to this Desmos graph in the video description below and in the online lesson content so that you can jump in here and play around with these as well. So the first example we're going to look at is this question here. We've been asked to sketch the graph of y is equal to negative 2 tan x minus pi on 3 over the domain from x is negative pi to pi. The first things that we're going to look at, just like in our function study unit, quite often we have attributes of the graph. For our tan graph, what we really care about is what's the shape of our graph. We're going to think about that first. We also might want to care about what's the period and where are the asymptotes. I find that to be the easier place to start before we then also have a look at the y-intercept and the x-intercept. Although different people prefer different things, you can very easily go to the asymptotes from the x-intercept or vice versa. So whichever one you come up with, it's going to help us do the other one. All right, so our shape is our tan graph, which we know, and there's a reflection there. So we can look for a reflection, either a horizontal reflection or a vertical reflection. But in this case, there's one reflection there. So that means that our shape is going to look like this because we have reflected it vertically. We should know as well that if we had reflected it horizontally, if there was a negative here instead of here, then we'd get exactly the same shape. And if there was a negative in both places, then the reflections essentially cancel out and we get back to our basic graph. So that's our shape. Next thing is our period. What's our period? We know that our period is equal to, it's a tan graph, and the base period of a tan graph is pi. So in this case, it's pi on n, not 2 pi. In this case, we can clearly see that n is our horizontal dilation factor, which is 1 in this case. So our period is equal to pi. All right, the next thing we're going to think about are the asymptotes. The easiest way to get the asymptotes is just to work out where one asymptote is, and from there work out our period. Really quickly thinking about it, we're going to have a graph that looks something like this, and we're going to have an asymptote. If we can calculate where one asymptote is, somewhere there, then we know that our next asymptotes are just going to be a period away and a period away, and we can do that for as many as we need within our domain. So working out that first asymptote is our key step. Next, how do we work out where our first asymptote is? Well, let's remember with our unit circle, our standard good old unit circle, whereabouts does tan have an asymptote? Tan is undefined at that pi on 2. That's the value for theta that is undefined. And so to work out, in any tan graph, to work out where the asymptote is, we essentially need to work out where our theta value is undefined, or rather where pi on 2 is the value inside the tan function. So to work out our first asymptote, let me undo that so I can create a little bit more space. So my first asymptote, I always find by essentially saying, well, pi on 2 is the value that is inside the tan function, whatever is inside that brackets of that tan function. So no matter how complex that is, it might be a dilation and a translation. We're just going to set that value there. In this case, it's x minus pi on 3 to be equal to pi on 2. And so now solving this, adding pi on 3 to both sides, gives me 5 pi on 6. And so that tells me where my first asymptote is. And from there, I can now also work out my other asymptote. Now, let's think about our domain. Essentially, we're sketching here and we're going from negative pi up to pi. 5 pi on 6 is very close to pi, so that's going to be somewhere around there. There's no point adding a period because that'll take us outside the domain. But if we subtract a period, we're going back pi from there. This is 1/6 of pi to get from there to our edge of our domain, so that means it's also 1/6 of pi to get down there. So we're going to get another asymptote at 5 pi on 6 minus pi, which is equal to negative pi on 6. I've done some explanation diagrams around that, but that was never going to be my actual graph. So let's now leave those as our two asymptotes. We've got one there and we've got one there, and we'll move on. And when we're sketching our graph, we'll include those. All right, let's think about our y-intercept now. This one's pretty easy, just like in all our function study stuff. We know that our y-intercept occurs when x equals 0. So y is equal to -2 tan of 0 take pi on 3. So tan of -pi on 3, we know we're going to be down there. It's going to be a negative value because we're in quadrant 4, and negative of whatever tan of pi on 3 is, which we can look up on our table of exact values, and we know that tan pi on 3 is √3. So this is -2 times and negative √3, which gives me an answer of 2√3. That's where my y-intercept is going to be. Now my x-intercepts, I'm going to take a shortcut with this one. One way that will always work for your x-intercepts are to do the first one, just like remember our asymptotes. Once we work out where one asymptote is, we can just add or subtract the period. It's the same method for x-intercepts. So once you've worked out what one x-intercept is, you can just add or subtract the period. And so you can just substitute in 0. It's solve for 0, but we don't have to find all the solutions. Remember, we're only looking for one solution, and then adding or subtracting the period sort of makes it easier. But in this case, we can also take an even better shortcut. You may remember previously in my earlier explanation, I stated that when there's no k value, when there's no plus or minus afterwards, translation upwards or translation downwards, we know that our x-intercepts occur halfway between our asymptotes. And that's the case in this situation. We know that between our asymptotes, and we've got two of them, so halfway between 5 pi on 6 is one asymptote and -pi on 6 is another. That's a difference of 6 pi on 6 because our period is pi. And so 3 pi on 6 each direction gives me 2 pi on 6, which is the same as pi on 3. And also, if we go 3 pi on 6 back from our -pi on 6 asymptote, we're going to get another one that's going to be at -4, -4 pi on 6, which is equal to -2 pi on 3. So those are my x-intercepts. I think I've got enough information to sketch this now, so I'm going to draw a neat set of axes, unlike all the messy ones I've been drawing so far, to try and explain some concepts. I've got all the information I need now, so I'm going to draw a neat set of axes, unlike all the messy ones I've been drawing while trying to explain concepts. Here, labeling our key points, like our edge of our domain, pi, pi on 2, -pi on 2, -pi. That looks roughly to scale, doesn't have to matter too much. What I like to do first is put on my asymptotes, which are going to be at 5 pi on 6. And -pi on 6. So I'm going to label those after I write them down. 5 pi on 6 and a vertical asymptote at x equals -pi on 6. Next thing to put in is my x-intercepts, which we have here at pi on 3 and here at -2 pi on 3. My y-intercept I can label, which is right here at 2√3. And from here we can certainly put in our shape. The first one is nice and easy to put in. Make sure we have a nice asymptote at each edge. This one we can start a little bit of a curve but not go all the way. A little bit of a trick here is to recognize that this section which happens from our asymptote to our endpoint, is actually identical to this section here. So we can just sort of copy that little part of it. So just try and get the shape about right. It also ends at exactly the right point as well. So we know that since this point here is at 2√3, a y value of 2√3, and this point here is a period away from it, it must also have the same y value. So that means that the y value here at our endpoint is going to be pi, 2√3. Putting the rest of this on, since we've also got this one here as a period apart, that's also going to be the same y value. And then we just want to sort of continue our curve from where we had it here. If we imagine that curve going down that way, just as this one went down that way, we can just sort of continue that curve there. It doesn't matter too much, but it's important to recognize that what we've got here is part of the period of a tan graph, and a symmetrical part. So ideally, if that bit joined up with that bit over here, then we'd have another whole period of our tan graph that should be identical to that period. So we're trying to create all these identical periods of a tan graph. It's just that one of them's interrupted and sort of goes off one end and starts on the other. I haven't labeled that point there, so let's label that point there as negative pi, comma 2 root 3. Let's double check I've got all my intercepts and asymptotes and endpoints labeled, and that's finished. Now, that took me a long time. I recognize that took about 12 minutes to draw a reasonably simple graph. That was because I was stopping and explaining a lot on the way. I'm going to do another example now where I'm not explaining as much as I go. I'm only going to just do the working that's required for the question and see how quickly I can get through it. Hopefully it should be down to just 5 minutes or so, which is about how long it should take you to be able to do it. Not immediately, but by the time it gets to your test or an exam situation. All right, so let's jump to another example. So this time we'll sketch y is equal to tan 2x plus 1 over the domain 0 to 2 pi. This looks reasonably standard. There's nothing too tricky. There's only 2 transformations, but they are a little bit different to that previous example. As I said, I'm going to try and get through this with minimal explanation of why I'm doing things as I go, just to demonstrate to the student what the standard amount of working out that you should require is. Right, let's start by thinking about the shape. Are there any reflections? No, so this is a standard positive repeating tan graph. Let's think about the period. We know that the period is pi on n. In this case, n is equal to 2, so the period is pi on 2. Next, I think about our asymptotes. Now, there isn't any translation here, but that dilation is going to affect it. I usually think about where my first asymptote is. Remember, by setting pi on 2 equal to what's inside the tan function. In this case, what's inside the tan function is 2x. Solving that for x means I have to halve both sides, so x is equal to pi on 4. That's where my first asymptote is. I then need to also add my period, being pi on 2, so that means I'm going to get an asymptote at 3 pi on 4. And another one, a period away, is 5 pi on 4, and keep going until I get past my endpoint, and that's 7 pi on 4. If I went any further, it would be 9 pi on 4, which is past my endpoint of my domain. All right, so they're my 4 asymptotes. Y-intercept, we know that it occurs when x is equal to 0, so in this case, y is equal to tan of 0 plus 1. Tan of 0 is 0, so that occurs at y is equal to 1. And let's also think about my x-intercept. Now, in the previous problem, I could jump to the conclusion that they were halfway between my asymptotes. This time I cannot, so I have to work them out a little bit more of an old-fashioned way. Let's set the y value to be equal to 0. That gives me tan of 2x plus 1. Subtract 1 from each side. Negative 1 is equal to tan of 2x. Solving whereabouts is tan equal to negative 1. We know that tan is equal to negative 1 there and there, where my base angle is pi on 4. So that's 3 pi on 4, or that could be negative pi on 4, which is outside my domain, or it could be 7 pi on 4. Doesn't really matter which one I pick, because what I'm going to be doing is adding the period to it each time. So in this case, I'm going to be saying 2x is equal to 3 pi on 4, that first one. Just one of my solutions, that's all I need to find. I'm not worried about all of them at this stage. Now x is equal to, I'm going to solve for x, which is 3 pi on 8. And now I know that if that's one of my x-intercepts, my other ones must be a period away. Period being pi on 2, which is 4 pi on 8. So I'm also going to get solutions at 7 pi on 8, and at 11 pi on 8, and at 15 pi on 8. And hopefully, if I go any further, I'm past my endpoint. That's nearly 16 pi on 8, which is nearly the endpoint of my domain, 2 pi. So I'm not going to go any further. That's enough to sketch it. Let's draw a set of axes, I'm going to draw them with that sort of shape this time, knowing that my domain doesn't have to go below 0. So in this case, I'm going to start there at 0. Here's 2 pi. We're going to draw it at pi, and pi on 2, 3 pi on 2. My y-intercept is 1, so we're going to start there somewhere and go upwards. Now, since that's an endpoint, I might as well label it now, which is going to be at 0, 1. Next thing to think about are my asymptotes. My first asymptote occurs at pi on 4, which is there, halfway between 0 and pi on 2. I might as well label that now. Vertical asymptote at x equals pi on 4. My next one occurs at 3 pi on 4, which is going to be there, and then every period away. So I can sort of reasonably quickly do that. Sorry, my straight lines aren't as straight as I'd like them to be on an iPad. Yes, it is important that you label each of these. That might seem very annoying and time consuming, but it is assumed, unless a question says do not label, which I don't think you'll get, it is assumed that you'll be labeling all your asymptotes. All right, now we can, before I go any further, let's put our x-intercepts in. We know that they occur at 3 pi on 8. What's 3 pi on 8? That's a little bit less than 4 pi on 8, which is a little bit less, which is the same as pi on 2. So we're getting one there, a little bit less than pi on 2, and then one a little bit less than pi a period afterwards, a little bit less there, a little bit less there. And so what I like to also do, thinking about how this graph has obviously been translated upwards, so that 0, 1 point there is not only my origin, but every period afterwards is going to be the point where the gradient changes, going from getting less steep to getting more steep. I can now put my graph in like that, and then try and get through this point here, and also that point, but then changing my gradient to getting more steep like that. So there's a delicate sort of operation here. The important point is to note that this point here is really the center of our graph. And it's also where we're going to finish, since our domain is an even point. So that point there is 2 pi, 1. And we're done. So you can see that it didn't take that much time when we don't stop and explain everything on the way. I'm going to do one more example that is going the other direction. Can we work out how to go from a graph that is presented to us to the equation? So in this example, we're going to look at this graph and try and determine what function might fit it. Usually if this happens in a test or an exam situation, you'll get given an equation template. You might get given something like a tan n lots of x minus b plus c, or h and k, and try to fit it in. In this case, we're not. Now, the reason they might give you a template like that is, you know, if they give you a template and it doesn't have an n value, that our n value is 1. Or if it doesn't have a b value, you know the b value is 0. So you might often get hints from the template that they present to you. In this case, no template is provided, so we can write our own. This is what we are going to try and fit our function to, although it's got to be a y equals or a function. All right, so what do we know? Well, we're given 2 vertical asymptotes, and we know that there must be a period between them. Thus, the period is equal to 2 pi, because this one's 10 pi, take 4 pi gives me 6 pi on 3, which is 2 pi. And we also know that our period is equal to pi on n. Thus, we can very easily work out that n needs to be equal to a half. So if n is a half, what else can we work out? Well, we've got enough information. We know that a and c here are going to not affect our asymptotes at all. So if we just think about what we can do from our asymptotes, we know that this b value is going to be we should be able to work out just from the knowledge of our asymptotes as well. Now, normally we've got an asymptote for our tan graph. We've got an asymptote at pi on 2 and at 3 pi on 2. That is going to get dilated by a factor of a half. So then now we're going to, if I undo those red lines, we're now going to get an asymptote at pi, and at double 3 pi on 2 is 3 pi. And you can see that this translation, we've then translated a certain amount to get our asymptotes from there to there. How much? Well, this asymptote was previously at 3 pi. It's now at 10 pi on 3. 3 pi is the same as 9 pi on 3, so this is translated across pi on 3 after we've done our dilation. So thus we know that this can be written as tan of a half lots of x minus pi on 3. That translation is happening after we've done our dilation. We still have to work out what A and C are, and these two can be a little bit tricky. So how do we find A and C? Well, depending on what information you're given, you'll need to use a different method. In this case, we're given that information there, which should give us a hint that we've identified there's been a translation that is pi on 3 units to the right. And so given that this asymptote here has translated pi on 3 to the right, and this one here is translated pi on 3 to the right, it's interesting to think about this point here, because we know that pi on 3 to the right puts this at an x value of pi on 3. So this is the point that was on the y-axis before that translation. That means if it was on the y-axis before the translation, this dilation here didn't affect it. So if that point was on the axis before the translation happened, that means that it must be what was originally the origin point. Since it's translated upwards, that means that gives us our C value. Now that's not always the case. There's a lot of logic behind me writing this down here, that C is going to be root 3 on 3, because we know that essentially this point started there, and we know that because it wasn't affected, it wasn't dilated before it was translated pi on 3 to the right, and then it wasn't dilated vertically by our A value before it was then translated root 3 on 3 up. That's the only possible way it can get to that point. So thus we know C is equal to root 3 on 3. We still have to work out our A value. Our A value is our dilation factor that must happen before that translation. That means that that point there, that pi on 3, root 3 on 3 point, isn't going to help us, because that point was on the origin when the dilation happened. So thus we need to pick a different point. Here's a really obvious one. What is the origin? So now I'm essentially going to, we worked out N and B and C, and now to work out A, I'm just going to substitute in a point. So in this case, I'm going to substitute the point 0, 0 into this equation here, and that gives me 0 is equal to A tan a half lots of x, which is 0, minus pi on 3, plus root 3 on 3. So from here we need to work out what tan of a half times negative pi on 3 is. We need to get our order of operations correct here. That's negative pi on 3, but we're halving it, so we need to work out what tan of negative pi on 6 is. Negative pi on 6 is down there. That gives us a base angle of pi on 6. And so we know that that's going to be equal to, we're down here, that's negative in quadrant 4. So this is going to be A lots of negative root 3 on 3 plus root 3 on 3. We're solving that for 0, so thus A is equal to 1. Plugging all those values in, I get a final answer of y is equal to tan lots of a half times 0 times x minus pi on 3 plus root 3 on 3, and I have finished.